so we got to make sure all our systems are good, and you know, enlarge the tank farm for liquid nitrogen and all that stuff. And thank goodness, because we powered right through it. It's a 100-day test, 24 hours round the clock for 100 days, and we pulled it off, and it went great. So then we shipped the telescope in that container on a big C-5 aircraft and sent it to California, where folks from Northrop Grumman had been building the spacecraft and the sun shield. And so we put those two things together. And then this is what the sun shield looks like deployed. It's 5 layers of really thin Kapton, which is a kind of plastic. It's like really fancy trash bag material with aluminum vapor deposited on it. And the 2 layers toward closest to the sun are 2/1000ths of an inch thick. The other 3 are only 1/1000th of an inch thick. And they had to be, we had to design these to take just the right shape and under tension when deployed, so that they blocked light from the sun, but they didn't redirect light into the telescope. Really fancy device. Over a, let's see, yeah, it was like a mile's worth of cable, 90 cables just to do the, to deploy the sun shield alone. 600 pulleys and mechanisms, it was crazy. So now it's built, so let's take it to space. So we put it on a ship and folded it up like it's going to be for launch, put it on a ship, and sailed it from Seal Beach in Southern California through the Panama Canal to French Guiana, which is where the European spaceport is. It's kind of Europe's version of Cape Canaveral. And the Europeans, as I mentioned, are partners with us, and one of the things they did, besides 2 out of the 4 instruments that are on the telescope, they provided the launch vehicle and the launch services. And so we flew on an Ariane 5, which is a really nice rocket that is very highly reliable. And so we're doing this. It's funny that that launch site, I like to say it's like the movie Papillon, but with rockets. That's actually where the launch site is. It's at the old penal colony, and just offshore you see Devil's Island. So we got on top of the rocket, and then the rocket's leaving the building where that final assembly was done, and here's launch. Christmas Day last year.
And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
And then 26 minutes later, after powered flight was over, we separated from the launch vehicle. You see the Horn of Africa and the Arabian Peninsula here. So 26 minutes, we're a quarter way around the world, and we separated. And we're watching this in real time, which is pretty cool. And we see the solar ray come out, which we didn't expect. We thought this might take a while to do. But because the Europeans gave us such a nice launch, it was perfectly done, basically. And the satellite came off the rocket perfectly straight. That the this deployment, which was the only one that was automated, everything else was commanded from the ground. We this came out as early as it possibly could, and we were thrilled to see it. And then we knew we were making electricity out of the sunshine. It was really important to get that solar ray out, because the battery we were on since 11 minutes before launch had like 7 hours of life on it if we didn't get the solar ray out. So getting that solar ray out and getting power positive was huge. And then this is 2 weeks shoved into a minute and a half. Those 53 major deployments I mentioned, you're going to see them all here. Again, 178 release devices, 295 single point failures. They all had to work. So we spent much of the last several years on the program rigorously testing this thing and making sure that when we folded it up for the last time, we did it right, and we knew exactly what we had done. Because every time we tested this thing and had to fold it back up, it was like a reassembly procedure. So it's like an Etch-a-Sketch. We kind of erased all the work we did with the previous tests. So we had to make sure that last stow was perfect. And here you see most of the deployment activity is associated with the sun shield. So these telescoping booms came out and dragged with these cables that are like only steel cables, only a millimeter thick, pulling them out. And so one thing that made this super challenging was these membranes are really thin, they're floppy. If you don't control them and all the cables used to pull them out and tension them, they can get snagged very easily in the weightlessness of space because they'll just go where they want. So the design incorporated all these tiny little party favor devices, really ingenious and simple, that we never had a piece of membrane or a cable that was unconstrained over longer than about an 18-inch length. And that way we always knew where things would be and they wouldn't get entangled and we wouldn't have a snag, because that would have ended the mission. And then the telescope unfolded, and that's rigid, so it was kind of like straightforward. That wasn't easy, but it looked easy compared to sun shield. And then it took us about a month to get to our destination in space, which is called Lagrange Point 2. So Louis Lagrange, famous mathematician, he said, hey, any three body problem, if one of the bodies, there's no single solution, it's a chaotic thing. So, but if one of those bodies is gravitationally insignificant, guess what? There's 5 places where the gravity of the 2 big bodies kind of create these happy places where it's easy to put something. And they're called Lagrange points. And so a lot of satellites that study the sun go to L1 because they can just look at the sun all the time and point their antenna at Earth and tell you what's going on. L2 is a great place for Webb because you can always keep the sun, moon, and Earth on one side and see basically half the sky the rest of the time. And like I said, if you just wait 6 months, you'll have seen the whole sky. And the L4 and L5 are actually kind of like garbage collection points. The other 3 are metastable. It's like trying to balance a BB on a saddle. But L4 and L5, there's actually there's rocks that are kind of stuck there, asteroids. And but yeah, and Webb's not the only thing at L2. There are some other, it's the equivalent of the mountaintop for ground-based astronomers. There are a few other spacecraft out there. And we had to get away from the Earth because the Earth's a big room temperature object. If we were in low Earth orbit like Hubble is, we would never get cold. And you'd be going from daylight to nighttime every 45 minutes. And that just wouldn't work. So L2, you're about 1 million miles away, and it's a benign thermal place, and you can get really cold. And that just shows how we can see almost half the sky at any given time. Just wait a few months, you see everything. So this animation really helps visualize it. So L2 is this virtual point. We're actually orbiting it. It's easier to orbit L2 than actually sit at L2. And besides, if we sat at L2, we'd be eclipsed from the sun by the Earth. And then one thing this is inaccurate about is the Earth happens to subtend half a degree of arc from 1 million miles away. So it looks to be the same size as the sun, and it would perfectly block out the sun, just like the moon just happens to be at the right distance from the Earth right now, that it perfectly blocks out the sun and causes an eclipse. But that's our orbit. And then here's a little bit about alignment. So this thing, it wasn't aligned when we launched it. We had to the mirror, to be able to fold it up, we couldn't make it one big mirror, so we made it in pieces. But then the trick became, well, we gotta line those pieces up to within a fraction of a wavelength of light when it's in space by remote control. So all those 18 primary mirror segments and the secondary mirror, which is the second thing that light comes in, hits primary, comes back to the secondary mirror, and then goes back towards the instruments. Those are movable, and we had to line all the 18 segments together as one optic. So the first image we got was 18 random images of the same star. And then we moved each mirror in order to go, oh, which one goes with which image? And then once we figured that out, we arrayed them into a pattern like the primary mirror has. and then we stacked them all on top of each other. But now, yeah, you've got all the mirrors lined up, but they're not surfing the same wave, so to speak. You know, one mirror can be here and the other surface can be here, and you want all their surfaces to match so that the whole mirror is coherently phased. And so there was a lot of software and a lot of work involved to develop this process that, you know, now is no big deal, but it was a huge challenge a long time ago. And future telescopes that are going to get launched from the ground and are, you know, segmented mirrors like this, they'll take advantage of this technology. And this is what an alignment image looks like. So if you're an optics person, this is like, oh wow, that's awesome. So the reason it has spikes is because of the hexagonal honeycomb nature of the main mirror. Light is a wave, and you know, if you pass a wave through a hole, it doesn't just go like a straight, you know, thing. It diffracts, and waves that their peaks fall on top of each other, they constructively interfere, and where a trough and a peak of another of two waves coincide, they destructively interfere, right? And you get a flat wave. It's like, anyway, sorry, I'm rambling, but the light's a wave, so it'll diffract, it'll interfere with itself, and because we have this beautiful mirror made of all these, looks like a big honeycomb, we get diffraction spikes. You'll see the same thing in camera shots that people have, because the aperture of the camera, even though it's maybe a single lens, the aperture stop has a shape to it, and so you'll get these spikes. Hubble has 4 spikes because the cross piece that holds its secondary mirror is in front of the main mirror, and even though it's one big solid mirror on Hubble, but with Webb you get the 6 spikes, and then the reason you see this is because of that tripod that holds the secondary mirror that's in the way. So it shows up on really bright stuff, but it's easy to track out, and it's pretty much an artifact of any optical system. But one more thing I want to say about this image is, you know, we're trying to find stars that were all by themselves to do these alignments, and everywhere we look, we're seeing galaxies that maybe nobody's ever seen before. There's no dark spot in the sky anymore with Webb. You can't point it anywhere and see something dark. And then this is how the fields of view of all the instruments look on the sky. So if you imagine the whole screen looks like this crowded star field, which is a picture of the small Magellanic Cloud that's or no, it's a large Magellanic Cloud. It's a dwarf galaxy that orbits our own galaxy, and it's just chock full of stars. These are like windows. Like this whole screen would look like this, but each instrument is like a window into a part of the sky. And these are all the fields of view of the instruments. And then this is the best part, using Webb. So Webb is operated from Baltimore. The observations are actually competitively solicited in annual cycles, and we're executing cycle 1 now. So the people whose observations are getting executed, they proposed them like a couple of years ago, and then they were selected in a double-blind process to try to take institutional bias out of it and things like that, because scientists looking at other scientists' stuff, right? And so it's an interesting process to make sure that there's little bias in it. It's all about the science potential of an observation. And they're all planned, and then basically roughly every week we code them, the observations, they get scheduled together, and then they're uploaded, and the software on the observatory is smart enough to basically execute them quasi-autonomously. And then the raw science comes down, and it's all processed on the ground. It comes down by radio to Earth. Webb's about 5 light seconds away, so it takes 5 seconds for that signal to get here. And it comes down on Ka band, which is almost the same frequency as DirecTV. So it's like ESPN, but for science. And then the data and findings become either public right away or shortly thereafter. And then engineering-wise, we're almost always in touch with the telescope, and we get telemetry down. We have sensors all over this thing that tell us what temperature it is and how's it doing, and that's how we know how the spacecraft is doing, and that's engineering data, and that comes down on a lower frequency, again to the Deep Space Network, which is a network of satellites spaced there's 3 of these around the world, so at any given time, one of them's always in view, because Webb's kind of hanging out there in the midnight sky, but it's midnight for anybody, and the Earth's rotating, and Webb's kind of out there, so to make sure we always have an antenna on it, we've got these things spaced around the world. And then, whoops, this is just a picture of our mission operations control center. This is the MOM, the mission operations manager, Carl Starr. He was our MOM for the commission, the 6-month commissioning of this machine. And then now I get to show you some pictures. I'm almost done. So you may have seen some of these, but on July 12th, scientists had been thinking for years, what can we select for observations that will be beautiful and showcase the scientific capabilities of this machine when we reveal it. And so this is the Southern Ring Nebula, which is really beautiful. It inspired some artwork by Ashley. That piece is here. And this is that nebula in near-infrared light. This is in mid-infrared light. And at these longer wavelengths, the light can actually penetrate the dust that's enshrouding stars in here. And it reveals the star that's actually the source of all this stuff being blown off, and it's that red star. And then I mentioned spectroscopy. So this is kind of what a spectrograph looks like. Wavelengths, it's light intensity versus wavelength. And this is of a planet that's kind of like Jupiter, but it's orbiting its parent star very, very closely, so it's really hot. So this is basically saying this Jupiter-like planet orbiting really close to its star is really hot, and its atmosphere is full of steam. And then this is something called Stephan's Quintet, and it's a group of galaxies about 250 million light years away, a little farther than that, and they're gravitationally in this dance. And when galaxies interact like this and collide, they create a whole bunch of starbursts, and there's a lot of science in this image. And then this is pretty cool. This is a deep field image. Webb in 12.5 hours stared at the darkest part of the sky it could see, and this is a pretty small part of the sky. It's like holding a grain of sand at arm's length. And there's thousands of galaxies in here, and some of them are distorted because they're actually multiple images of the same background galaxy that got distorted by a galaxy that's closer to us that acts like a gravitational lens, because Einstein figured with his general relativity, figured out, hey, mass warps space and it can bend, and light travels in a straight line, right? But it's traveling through warp space, so it's like bending light. And we can use these foreground clusters of galaxies as nature's magnifying glass to see things that are very far away and behind and magnify them. So it's kind of a cool shot. And then lastly, this one seemed to capture the public imagination more than any other. This is the Carina Nebula, which is a cloud of dust material left over from the deaths of previous generations of stars. And new stars are kind of blowing it away, and new stars and planetary systems are being born in the knots of this cloud. And it's it's scientifically, it's like really cool, but just from a appreciation of its beauty standpoint, it's really pretty. And then here's some more recent observations. The Tarantula Nebula, which is a really interesting region just outside our galaxy. And this is just really beautiful. There's so much science in here. I gotta leave Elaine time to talk, so I'm not gonna talk about it. This is the same galaxy in 3 different views. This is visible from Hubble. This is from Webb at longer wavelengths, and it's showing basically the dust skeleton of this galaxy. And then when you overlay them, you get this in the middle. The one on the right is cool. And here's Jupiter in infrared light. And it looks different because, the the material that makes up Jupiter presents itself differently in the infrared than in the visible spectrum, but it is pretty. I mean, you can even see Jupiter's ring, which is incredibly tenuous, not like Saturn's, which is really obvious. And then here's Neptune. So Neptune with from Voyager when it flew by many years ago, Neptune from Hubble, and Neptune in the infrared. And Neptune's very bright in the infrared because its atmosphere, the nature of its particles, it just reflects infrared light really well. And you see the rings, which are beautiful. All the outer planets have, the 4 outer planets, 2 gas giants, 2 ice giants, have rings, but Saturn, of course, is famous for it because you can see them. But these other ones are hard to see without modern equipment, but it's just a beautiful image. So, and we can actually take images of planets around nearby stars. So the white star is actually where the parent star is, but we have things on the instruments called coronagraphs where you basically put a spot in front of that star so you can block out its light and cut down on the glare and see what pops out. And it's kind of a crappy image, but hey, it's an image of an exoplanet. That's pretty amazing. And lastly, back when Hubble took this picture here, it's called the Pillars of Creation. This is the Eagle Nebula, which is a pretty neat object that as an amateur astronomer you can take a picture of. Probably won't look this good, but this is visible. But in infrared, this is a lot of dust, and there are stars and planetary systems forming inside, but you can't see it because the dust grains are on the order of the size of the wavelength of visible light, and so it's opaque to visible light. But at longer wavelengths, you can penetrate these dust clouds and see what's inside. And you certainly see that the resolution is amazing compared to Hubble, but you see more, and the two are very complementary. And there's just so much science here that scientists can mine for a long, long time.
Yeah.
So, I'll just end with one last video. And I do want to say that, Webb was conceived and built to do certain things, from seeing the very first luminous objects to form in the universe, to galaxy evolution, to sniffing the atmospheres of exoplanets, and maybe even looking for the conditions that we understand that make life possible. But I really think that its greatest discoveries are going to be answers to questions that we haven't even yet thought to ask. And so with that, I'll leave you with this.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights.
I hope you can hear it.
We've crossed the solar system and sent ships to the stars.
Oh, shoot. I ruined it. Hang on.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
Thank you. It's really my pleasure, and I'm happy to take questions or get Elaine up here and we'll both answer questions later. But thank you very much. Really appreciate your attention.
Okay, so thank you, Paul, again for that amazing talk. Chills. That's a great highlight reel for the telescope. Okay, so we're going to take a quick break. Everybody can refill their cups, and then we're going to get Elaine Stewart up here, and we're going to do her talk next. So 10 minute break, maybe? 5? Yeah, 5. 5 minute break. Great. Excellent job. That's cheating. I know. I know. I was tearing up.
I'm glad I just turned up the sound.
Yeah. No, I went back and I was like, we're gonna. As soon as I saw the first little bit of it, I was like, oh, we gotta crank this up.
Okay, so we're switching out computers. We actually put my presentation on his flash drive, so I think